Hello, class. Welcome to lecture 17. So today we are talking about the algebra of sets. Scary kind of phrase, but what this really means is we're just going to talk about how the operations, the ways to combine sets and turn them into other sets, how they interact with each other. So that's what this is really about. So how set operations interact. That's the idea. So first I'm just going to summarize the rules before I try to prove them. And there's too many to prove all of them. So unfortunately, we're not going to do that. Okay. So here are, starting from like the more basic ones, a couple of them. So remember that this symbol here means the empty set. And it's sort of interesting because empty set sort of acts a lot like zero. If you think of it acting like zero, then it sort of tells you how intersection and union sort of act like addition and multiplication. Whoops, I was just mindlessly writing, so I wrote that down wrong. I should think while I write. There we go. So let's think about, first of all, why these are both true and what they're really saying. So the first one is saying, I guess I'll number them, that the intersection of a set with the empty set is just the empty set. So that makes sense because what does a set and nothing, a set with nothing in it, have in common? Well, they must have nothing in common. So their intersection is just the empty set. On the other hand, if I add to A nothing, it's going to stay the same. And so what this tells us is sort of like the empty set sort of acts like zero, and intersection sort of acts like multiplication. So if you do like 5 times 0, you get 0. And then union sort of acts like addition because it looks like you're doing A plus nothing equals A. So this is sort of like X. I guess I should use X because it looks like times. I'll just think of a different letter. A times 0 is equal to 0. And this is sort of like A plus 0 equals A. So it's not wrong to think of intersection of sets as sort of being like multiplication between numbers, and union of sets as sort of being like addition of numbers. And so what's interesting is whenever you have operations that combine things, it's always a good idea to compare it to the operations that you already know about, like multiplication and addition, and see what kind of properties are the same and what kinds are different. So let's do another one. So A intersect A, what should that be? Well, what do A and A have in common? A. So in this way, it's not like multiplication because this is sort of like saying that A times A equals A always, but that's definitely not true. That's only true for like 1 and -1. So not true. So this is a way in which intersection of sets is different from multiplication of sets. Okay, what about A union A? Well, again, you're not adding anything new. When you union the same set together, you don't double count. So you just get A back, and this is sort of like saying A plus A equals A. And again, that's not true for numbers. So this is where addition is not like union, and multiplication is not like intersection. So these ones, I think I proved this one last time, or I'm going to prove it this time. I don't remember. But in any case, this is called a commutative law, and it's because, I don't know why it's called that, but it means you can switch the order of the operation, and it doesn't change what you get. And so this is sort of like saying, so A times B equals B times A, and this is true for numbers. And if I do union instead, same thing. This is sort of like saying A plus B equals B plus A. That's also true for numbers. And these are both called commutative laws. These are both also true commutative laws. These are both also similar to laws that you get in logic. If you think about and sort of as being like intersection, and or sort of being like the union, you get these same laws. Okay, the next ones are the associative laws. Oops, I gotta write them before I write the name. Oops, okay, need to do that. So the associative laws are all about what happens when you have more than two things being stuck together. The point is that you could do these two first, and then you could do the next one. So you could do A union B, and then union that result with C. But you could also instead stick B and C together first, and then stick that with A. And these should be the same, and they are for numbers too. So I guess I was using union to be sort of like addition. So this is also true for addition of numbers. It's very weird when this rule is not true. It's very hard to think of operations where this does not happen. It's a very common rule. The only example I can think of on the spot is sort of like if you like cook something, if you like stick two ingredients together and then stick the third ingredient together, it might be different than if you stick the last two together first and then stick the first one in. Okay, but if you go on to learn higher math, then you'll learn about actual operations that don't obey the associative law. That's always more interesting. Okay, so then intersection obeys the same law, same idea. And so does multiplication of numbers. A times B times C is the same as A times B times C. So these are called associative laws. And a lot of things in life obey them. Commutative laws are a little bit easier to find examples where it doesn't happen. So you have to learn a little bit more fancy math to see it, but it comes up sooner than associativity not working. One example is you could, never mind, that's too much to describe. Okay. All right, so then whenever you have two operations that are both putting things together, so like we have addition and multiplication for numbers, here we have union and intersection, you want to see how they interact with each other. And so that always means checking how one distributes over the other, if it does, and in this case it does, just like the logical symbols distributed over each other. So this is going to be A union B intersect A union C, and then the other way will also work. So this is, again, very different from numbers, just like the logic ones were, because in the number land, addition and multiplication do not distribute over each other. Only one distributes over the other. Here, they both distribute over each other. This is called the distributive laws. So you should compare, this is sort of why you should compare union, well, actually, no, sorry. We already did that earlier, but let's just compare the laws. I keep changing the colors. Let's compare to the fact that A multiplying into an addition does distribute the same way as these distributive laws work, but the other way doesn't work. So that's a bit weird. That makes sort of, it's nice when things are symmetrical. So it's, numbers are actually a bit weirder than sets in this sense because you only have one distributing over the other and not the other way. This doesn't make sense. Okay, I guess I shouldn't put no and not equals. There. Okay, so that's how they interact with each other. And then another thing that you can sort of think about as an operation is the complement. And you could sort of think about that as negating a number. It's very similar. So if I do a double negative, the complement of a complement, that should just take me back to the original. And that looks very similar to this law. Negative A is A. And then the weirder one is how do you distribute a negative across the operation? So this is very much like De Morgan's law for logic, which was instead of the C, it was a negation. And what it did was it negated each term and then flipped the operation. And that's what it does here too. So this is very different from how you distribute a negative. Here, you just distribute the negative. You don't turn this plus into multiplication or anything. It's very different. And then the opposite is also true. In the other way. So just like that. Again, that's way different from how you would distribute. If you try to distribute a negative through multiplication, well, you don't distribute it at all. It just becomes negative AB. It doesn't become like negative A plus negative B or something. So very different from how the operations between numbers work and negatives. Okay, and then, so these are called De Morgan's laws, just like they were called for logic. De Morgan's laws. And I mean these two things, not the little stuff in between there. And then the last one, this is not really a law, but just another way to think about A minus B. Remember we defined that? It's really just A intersects B complement because it's just the stuff that's in A and the stuff that's not in B, which is literally A intersect because that's what and means, B complement because that's what it means to not be in B. Okay, so that's a summary of the laws that govern how unions, intersections, and complements all work together. Very similar to the logic laws, sort of similar to the number laws with some small differences as we've seen. Okay, so these can all be proven by doing subset inclusion of each other, meaning you show that each side is a subset of the other side on the equal sign, and we'll do a few. Okay, so we will prove a few. So I think, yeah, I definitely did this one last time, just to remind you. Definitely did one of these two last time, and then you were supposed to do the other one in the lecture problems. So it's going to be very similar to those, the ones that we do today. So here's one of them. Proposition, given 3 sets, A, B, and C. We're going to prove the distributive property because that's sort of the most interesting one. And we'll do this one. The other one will probably work just the same if you just think about it the same way. Okay, so we'll prove that unions distribute over intersections, and this is the result. Okay, so how do you prove set equality? Remember that means basically two proofs. One where you let X be in one of the sets on one side. So I'll start on the left here. And then I got to show that as a result of it living in there, that it's automatically in the other one. And remember, what this shows is that everything inside the set on the left happens to also live in the set on the right. And so what this does is it shows that the one on the left is a subset of the one on the right. So that's what this does. And then we got to do the other way to show that they're subsets of each other, which means that they just contain the exact same elements, which is what it means for two sets to be equal. Okay, so a lot of work to be done. All right, so since X lives in this set that we said it lives in, what can I say from that? What can I actually write down? Well, it means that X lives in A or X lives in B intersects C. That's what it means for X to be in that set, because that set is the union of two sets, and this is what it means for a set to, an element to be in a union. It means it's in one or the other. So then we sort of have cases, because X can be in either one. So let's think about what happens. I guess I'll actually write down the phrase cases. If X happens to be an A, if we're in that situation, because it's got to be one or the other, then, well, I got to think about my goal. I got to get over here. So I need X to be in there. Well, if X is in A, then guess what? X is in A union B automatically, because to be in the union means to just be in one or the other. So if it's in A, then I've already got this covered. I'm in there now. And then same idea here. So if X is in A, then it's in there. And also, it's in here, because again, to be in a union just means to be in either one. So being in A is enough to be in the union. So now it's in both of these sets. If it's in both sets, that means it's in the intersection. Okay, so that proves the conclusion, what we're trying to show, in the case where X is in A. But we also have to consider what happens if X is in the other set instead. So if X is in B intersects C, then I still got to show the same conclusion. I still got to show that thing in the red box. Okay, but what can I say immediately? Well, X is in B intersects C. That means X is in B and X is in C. That's what that actually means. So now I know that X is in B, and I'm trying to get it to be in here. Well, same idea as before. Because X is in B, it's automatically in B union A, or A union B, just because of the definition of union. It's in one or the other. That's good enough. And the same thing will happen because X is in C. X is going to be in A union C, because again, it's in one or the other. It's in C. That's enough to be in both. So now X is in both. X is in this thing, and it's in this other thing. That means it's in their intersection, because it's in both. That's what intersection means. So again, we've proven the conclusion, and we've proven it for both situations that occur when you let X start off by being in here. Okay, so that shows one direction. So now let X be in the other set, and show, as a result of that, that X is in the first set, which was this one. So same idea. We're just going to expand upon what it means for X to be in a set, and then we're going to get somehow to showing that x is in here. Okay, so since x is in this thing, what can I say? I'm not doing any fancy tricks, I'm just saying what happens. Well, it's in an intersection, right? So that means it's in both. So it's in this guy, and it's also in this guy. So this one's a little bit trickier because I have two pieces of information. I have x being in two different sets, but each of those sets are a union, so I can still actually break this into cases. So the first case is, what happens if x is in A? Because it's in A union B and A union C, it's possible that this could occur. This isn't the only thing that could occur, which is why it's one case, but it could be in A. So if it's in A, then, well, let's think about where I'm trying to get to. I'm trying to get to here. Oh, but that's a union of two things, one of them being A, and x is already in one of the things in the union, so it's automatically in the union. So x is automatically in there now. And so that ends the proof for that case. What's the other case? There's only two cases. X could be an A, or it could not be an A. Those are the only two situations that could occur. So if x is not in A, but it is in the union of A and B, that means it's got to be in one or the other. This must mean that it's in B instead. So if it's in the union, but it's not in one of them, it's got to be in the other one. That's the idea. Similarly, since x is in this union, oops, not that one, this one, A union C, but it's not in A, then it must be in the other piece of the union. So what we have here is that x is in B, and it's also in C, in this case where x is not in A. So now we look to our conclusion that we're trying to get to, and aha, we have that x is in one piece of the union. It's not in A, but it is in the other piece of the union. It's in B intersect C, and that's enough to show that x is in the union. Okay, so in either case, and this covers all situations, right? Because x is either in A or it's not in A. Those are the only two possibilities. And in either case, we get the conclusion following from the hypothesis. So therefore, the statement is true. So we're done. A union B intersect C equals A union B intersect A union C. And again, because this, I'll just do a super zoom out. So this was all showing that the right side was a subset of the left side. So that's what this was showing. As opposed to up here, this was showing that the left side was a subset of the right side, so they're subsets of each other. So together with these two proofs, we've shown that the sets are equal because they're both contained inside of each other. So the only way that could be true is if they're the same set. So that's the end of the proof, but I would like you to compare it to this little phrase. If I say x is less than or equal to y, and y is less than or equal to x, what can you conclude about x and y? Well, they just have to be the same number. It's the only way that could be true. Same idea behind these subset proofs. Okay, all right, so that's one of the distributive properties. Let's do a De Morgan's law, just for some extra practice, we'll do one of those. So given two sets, A and B, the statement is that if I intersect them and then I take the complement of that, it should be the same as if I complement each of them individually. Oops, one of those should be a B. And then I switch the intersection to a union. Okay, so let's prove this one. Okay, same idea. I'm going to let X be in one of the two sets that I'm looking at. So this one's the one on the left. Then I'm going to show, as a result of that, that X is in the other set. And I'm going to do the opposite as well. But let's just do one at a time to not be overwhelmed. Okay, so we're just going to expand. Complements sometimes make things a bit more confusing because you have to think of in terms of negations quite a lot. But I think we can do it. So since X is in here, what can I say? This means, what does it mean to be in the complement? One thing is it means that it's not in the actual set. So it's not in A intersect B. And if I just write out this set, the definition of it, remember what that means. The intersection is the stuff that's in A and B. So to not be in there means that the negation, that X makes the negation be true. So X is either not in A or X is not in B. And the way I could think of that is, again, by thinking about, so this would be like scratch work over here, thinking about the fact that something not being in a set means that, so whatever this stuff happens to be with some predicate, means that the negation of that is true. And so the negation of this guy is that X is going to not be in A, or X is going to not be in B, because that's how negation distributes through logical statements. You negate each piece, and you change the ands to ors, and vice versa. So that's why. Okay. It might also make more sense if you just say it in English. X not being in the intersection must mean that either it's not in A or it's not in B. And that's the same as saying it's not in the intersection of the two. Okay, so then this means what? Well, this is actually the end of this part of the proof, because X not being in A actually just means X is in the complement of A, or X not being in B just means it's in complement of B. Which means that's the definition of union. It's in one or the other, so X is in the union of these two sets, which is what I wanted to show. Okay, so now the other one. So now I let X be in the other set first, and I show as a result that X will be in the set I started with. Okay, so let's see. It's just going to be the same proof but backwards, really. So since X is in here, this means it's literally going to be the same proof backwards, that X is not in A, or X is not in B. And this means that X is not in, so I'm just taking out that negation, A and B. So it's in the complement of A and B. I guess I'm sort of skipping a step here. So I could say that this means it's not the case that X is in A and X is in B. And then that means it's not the case that X is in A intersects B, which means X is not in A intersects B. So that's how I'm actually getting from here to there. Okay. So this ends the proof because I've shown this. I've shown that X lives in here as a result of it living in here first. So I've done both directions, so this ends the proof. Oftentimes, when a equality of sets proof sort of looks like doing the same proof twice, one in the reverse direction of the other, what that really means is you could also prove it by just starting with one of the sets and being very careful, and then just talking about it as it through its definition. So you could just say, what is this really? Oops, sorry, that should be a B. You could really just say it's a set of things that are not in A intersect B. And then you could just manipulate logical symbols to get to the other set. So X not being in A intersect B, that means it's not the case that X is in A intersect B, which means it's not the case that X is in A and X is in B, because that's what it means to be in the intersection. And then I could slip that negation right back through the and now I know how logical symbols work, so that means I'll even do one extra step that I would normally never do. So I'll send the negation through to both here. Then the and becomes an or when I distribute. And then negating X being in a set is just saying that X is not in that set. And so here I'm just manipulating the rules of the set to get from one to the other. And this is perfectly acceptable as a proof, although the other kind of proof is good too to practice, because you often have to do subset proofs where you just do one half of that proof that we did in one direction, and that's harder to translate into something like this. Okay, so we're almost done here. So what does this mean? This is just it. This is just saying that X is in A complement or B complement. That's just the set, A complement union, B complement. So this is perfectly acceptable as a proof too. Okay. And so set equality, you can often prove this way. All right, what else? So I'll make sure I'm not skipping a page here. Okay. So then we're gonna move on to some other rules that I want to note that is one other way to prove set equality. But then another way is sort of how we proved logical equivalences without having to do truth tables. And that was by using previously known logical equivalences. So you can use laws about set operations to prove new laws as well. So that's another way to do proofs. But the very like basic laws, the most fundamental laws like this one, you're probably not going to be able to prove like that. You're going to have to do it either this way or this way, one of those two ways. Okay, but once you get to like fancier laws, then you can just use previously known laws instead of doing any of this stuff. And that's usually a little bit easier because then you're just sort of manipulating symbols according to laws, which is just basically algebra, which is what you're more familiar with. Okay, but I want to move on to a different statement, and this statement I'm going to call a theorem because that just means it's super important. And it's sort of a new proof technique, but not really. It's more of a proof, a statement idea technique. I don't know. I'll fill you in when I get to it. Okay, so let A and B be subsets of some universal set. So I should have said in the other statements that the sets I was talking about were living in this universal set so that I could talk about complements, but I got a little bit lazy. Okay, so I didn't write that down, but that's okay. You don't really need to talk about the universal set to do those proofs. As you can see, I did them perfectly fine without the universal set. Okay, so then new type of statement. The following are equivalent. So how do you spell? Equivalent. So this is a phrase that math people say a lot, and sometimes they write this, TFAE, the following are equivalent, to mean that they want to say a bunch of if and only if statements. They don't want to say it that way because it'll take too long. So when they say equivalent, they do mean logically equivalent, which means that all the next statements that I write down are going to all imply each other backwards and forwards because they are equivalent. And then what they do is they just list the statements that they want to say are equivalent. So A being a subset of B is logically equivalent, the same as saying that the intersection of A and B complement is empty. Sorry, not empty. And 3, that the union of A complement with B gives you the whole set. Okay. So what we're doing is we're saying that these 3 all imply each other. And so what we're really saying is that A subset of B, if and only if A intersects B complement equals, does not equal to the empty set, if and only if A complement union B is equal to universal set. So remember how if and only ifs work. That means you have to prove that this one implies this one, and this one implies this one. You have to show that this one implies this one, and this one implies this one. But now we're saying all 3 are if and only if to each other. So I guess that means you got to show that implies that, and that implies that too. Is that all the relationships that there are? Yes. Aha, but you don't have to do this much work actually. So this green marker will come save us. What we're going to do is we're going to show that this one implies this one implies this one, and then we're going to show that this one implies this one. And that'll show all possible relationships. Why is that? Well, because if 1 implies 2 and 2 implies 3 and 3 implies 1, then you can get from any number to any other number. For example, how would I show that 3 implies 2? Well, 3 implies 1, which implies 2. So therefore, 3 implies 2. And you can get from any number to any other number. So how do I show that 2 implies 1. Well, I know that 2 implies 3 and 3 implies 1, so that gets me from 2 to 1. So I don't have to show all the red and blue arrows. I can just show 3 green arrows instead to show that they're all the same statement, that they're all logically equivalent. Okay, so proof. So in a statement like this where you say the following are equivalent, at the very beginning, you usually state your technique, which is what I sort of just talked about. So we will prove that 1 implies 2, and that 2 implies 3, and that 3, I know I've switched to the double arrow instead. It just looks better in proofs for some reason. Okay, so we're going to show these 3 things, and that will show that they all, if and only if each other, they're all logically equivalent. Okay, so first, to show 1 implies 2, we're going to use the contrapositive. So 1 implies 2 is saying if A is a subset of B, then A intersect B complement is not the empty set. Shoot, it should have been the empty set the whole time, not the empty set. Ah, crap! I didn't read it. I didn't think about it. I just read it and I wrote it down wrong. Okay, so this should be equals the empty set. Sorry about that. Luckily, I didn't start the proof yet, so hopefully it won't affect you too much. Okay. So that's why it's hard to video lecture, because sometimes you just read your notes and you don't think about them until you get to the proof. And then you realize that doesn't make sense. Okay. So we're trying to prove this, but we're going to use the contrapositive just because somebody decided that that was easier. You can try without the contrapositive and see. This becomes, so what's the contrapositive? You negate the hypothesis and the conclusion, and you switch them. So equaling the empty set becomes not equaling the empty set. Now you might ask, but I just negated an intersection. Shouldn't that like turn the intersection into a union because it's turning and into or? Well, no, because what I'm really negating is an equation. And when you negate an equation, the equality just becomes an inequality. But you don't negate the pieces of the equation. Okay, so this becomes if that, then A is not a subset of B. Now, I haven't really defined what it means for A to not be a subset of B, but it's not so bad to think about. It just means that A's got some stuff that's not in B. And hopefully that's going to be easy to show. All right, so how can I get from the if to the then? Well, we just write what things mean. What does this really mean for something to not be the empty set? Well, if it's not the empty set, that means it's got something in it. It has an element. So this means that there exists an element in the set. Because if it was the empty set, it would have nothing in it. But since it's not the empty set, it must have an element. So there exists an element in there. And since it's in an intersection, that means it's in both. And so what does this mean? Actually, this is exactly what we want. So X is in A, but guess what? It's not in B because it's in its complement, so it can't be in B. And that's exactly what it means for A to not be a subset of B. It's in A, but not in B. That means A has some stuff that B doesn't have, so it's not completely contained in B. So that's enough to say that A is not a subset of B. Okay, so that shows that 1 implies 2. So now we'll do that 2 implies 3. So we're going to, let's write it down first. If A intersect B complement is the empty set, then A complement union B is the universal set, the whole thing. That A and B both live in. Okay, well, I think this one we could just do straightforwardly. So let A intersect B complement be the empty set. And we're going to show the other part. So what does this mean? So if A intersect B complement is the empty set, well, that's sort of hard to imagine. So I guess it means that they have nothing in common. That's one way to think about it. Which doesn't necessarily help. So it's true, but it doesn't help. And that's the trick with these proofs is I'm doing them ahead of time, so you're not seeing where I mess up. But it's perfectly reasonable to say something like A and B complement have no elements in common. But then that doesn't really take you anywhere. So you say, okay, I'll try something else. So this is where I'm going to introduce the technique I was talking about before, which is we're going to use old rules to help us. So what we're going to do is we're going to use a previously established rule to help us. We're going to take the complement of both sides. So this is a sneaky trick that works really well here because the complement of the empty set is the universal set. So everything that's not in the empty set is just everything. So that's how we get that. So if X is not in the empty set, means that it's in the universal set. Okay, and then on the left, we're going to use the rules we just learned. So I complement both. And then I change the intersection to union, and then I cancel out my double complement. And that's the rule I wanted to show, right? Okay, so sneaky little tricks that you wouldn't necessarily think of without experience, but we're just gaining experience, so it's okay. All right, so now I got to show, so next show 3 implies 1 to complete the circle. So assume, or if, I'll just say if, so if this part is true, then A is a subset of B. Needs to be true as a result. So I'm just going to do a classic subset proof to show this. So I'm assuming my hypothesis is true. And then to show a subset proof, we let something be in the supposed subset of the other one, and then show that it's going to be in the other one. Okay. But now we're not showing this in a vacuum. We're assuming, first of all, that this is happening. Then we're letting X be an A. So we sort of have 2 pieces of information to work with. Okay, so what can we say? Well, we can't say too much. So that usually means that we have to invoke some tricky thing to make it work. So since X is an A, the trick here is to think about, well, maybe it's not so tricky if you look back at what you're assuming. If you want to somehow bring an assumption in, you got to think about how it could pop up. Well, I need the complement to pop up to talk about this. So what can I say about A complement with regards to X? Well, I know that the complement and the set are always disjoint. They have nothing in common. So if X is in A, it definitely cannot be an A complement. So maybe that helps. And then I can use my assumption. I know that U equals A complement union B. But the trick to this one is to think about the fact that every element lives in this bigger universal set that A and B are both subsets of. So I can also say that X lives in the universal set. And now I can bring in this extra assumption that the universal set equals A complement union B. And then what I really want to do is get X to living in B. Well, right now I have X living in A complement union B. So it's in one or the other. It's almost in B. It's in A complement union B, which means it could be in B or it could be in the other one. But guess what? We already said it's in the complement, or it's not in the complement. So when you have a union, if it's not in one, it's got to be in the other one. So I've shown what I wanted to show. Okay, so this proves the theorem because I've proven that 1 implies 2 implies 3 implies 1. So they all imply each other, so they're all equivalent statements. So what this theorem is saying is sort of just 3 different ways to think about subsets. So this is less about the algebra of sets, although we did use some algebra of sets by complementing the statement in 2. It's more about just other ways to think about subsets that might come in handy later. And this proof is nice because it gives us a lot of practice with various techniques. So I recommend going through it again. Got the contrapositive. We get doing a little subset inclusion. We get to work with the empty set. We do the algebra of sets. It's got like everything in it. Okay, so that's going to be it for today. I will see you next time.